Thank you. It's great to be here. Back up here in Berkeley. It's a nice place. So, yeah, the title of this workshop is Neoclassical Methods in Discrete Analysis. I had a little trouble trying to figure out exactly what that meant. But I decided that the closest topic I could give was one of my favorite things to evangelize about maybe is the connections between discrete mathematics and continuous mathematics, and really that they're not as far apart as we sort of traditionally make them to be. So most of us here are working at discrete mathematics, or maybe you might call it finite mathematics, quantitative mathematics. Discrete objects, finite objects, and we want bounds, explicit bounds. And that's one side of analysis, what's sometimes called hard analysis. And then on the other side of analysis, we have the opposite world, where you work with continuous objects, or infinitary objects, infinite, uncountable spaces, and things like that. And you often only care about qualitative results. So you don't care about bounds, you just care that something exists or something converges, but you don't specify rates or anything. And you've got sort of different people working in one world and in the other, but there's really a lot of connections between the two. So certainly there's a lot of analogies. So for example, in the continuous world, you have Riemannian manifolds, for example. It's a very continuous object. And there are isoperimetric inequalities and Chigo inequalities and so forth. And of course, in the discrete world, we now have all these nice analogs of these Riemannian geometry type results for various types of graphs and so forth. So there's certainly lots of analogies between discrete mathematics and continuous mathematics. But the connection is stronger than just analogy. There are really rigorous bridges that you pass between discrete objects and continuous objects, and in particular allow you to use results from continuous mathematics as a black box to prove results in discrete mathematics. So there's lots of examples of this that you probably already know of. So for example, in the discrete world, you might care about finite graphs, finite dense graphs, say. And you want to prove various theorems about finite dense graphs. And nowadays, we have this great tool, graph limits, which takes a sequence of finite dense graphs and produces out of it a continuous object, which is what's now called a graphon. Okay? Which is basically a measurable function on the unit square. And you can then use tools from continuous mathematics. For example, you can hit graphons with measure theory. Tools like the Lebesgue differentiation theorem, for instance, and you can use that to start to prove things back about finite dense graphs. For example, property testing, or the triangle removal lemma, regularity lemma, these sort of things. Another famous example, you might be interested in dense subsets of the integers. Okay, for example, you want to prove a Zemredi's theorem that all subsets of integers of positive density contain arbitrary really long progressions. And in the 70s, Furstenberg introduced the Furstenberg correspondence principle. Which connected dense subsets of the integers to measure preserving systems, actually, or positive measure subsets. Of measure preserving systems. So a measure preserving system is a probability space with a shift on it, some sort of measurable map which preserves the measure. And then once you have this set up, you can hit this with the techniques of ergodic theory. And also spectral theory and a couple other continuous tools of mathematics, like the ergodic theorem, for instance. And so he famously gave the second proof of Zemredi's theorem using ergodic theory methods. See more examples. You might be interested in, what are the examples? Okay, so you might be interested in discrete metric spaces. For example, Cayley graphs or something. And we have this tool to convert, if you have to take limits of discrete metric spaces and produce continuous metric spaces out of them. This is the tool of Gromov-Hausdorff limits. And then you can use lots of tools from continuous metric geometry to then, like Sophos spaces and whatever, to analyze the underlying discrete spaces. In particular, the continuous limits may have various group symmetries that only hold in some approximate or asymptotic sense in the discrete world. Okay, you might be interested in polynomials of bounded degree. For some discrete problem over some field, or maybe varieties, algebraic varieties of bounded complexity, almost the same thing. Variety. That's weird. I forgot how to spell. Okay. Of bounded complexity. So it's just a variety set out by a bounded number of polynomials of bounded degree, and you want to ask quantitative questions about these things. Like, for example, if I give you a bounded number of polynomials cutting out some set, some algebraic variety, it may have a number of components. How many components do you get? And can you bound the number of components in terms of the degrees of the polynomials that you have and so forth? And there's a way to take limits where you just, and in the limit, the qualitative analog is just polynomials and varieties with no bound on degree. And okay, so if I have time, I might talk about this sort of limit. Here, the cheapest thing to do is take an ultraproduct. And the point is that you can use tools. So over here, you can use the tools of this classical algebraic geometry. The algebraic geometry is the way it's classically presented is qualitative. It tells you, for example, a basic result is that every algebraic set can be decomposed into a finite number of irreducible algebraic varieties, but it doesn't give you a bound. It just says that there's a finite number. But once you have that fact, and if you just use the ultraproducts as a tool, you can get as a very quick corollary that automatically there is a bound. There's sort of a compactness theorem that says that in fact, once you know as a black box that every algebraic set can be decomposed into finite many irreducible subvarieties, you can conclude that in fact any algebraic set of complexity at most m, meaning it can be defined by at most m polynomials of degree m or something, can be decomposed into a finite number of varieties, and the number of varieties is bounded by only by constant depending only on m, and you can actually get that for free. And so there's lots of qualitative results about algebraic geometry automatically give you quantitative analogs, basically because in some sense, algebraic geometry is closed under ultraproducts. Okay, and then another example, which I think I won't have time to talk about, but okay, recently in additive combinatorics, we studied a lot of approximate groups. These are sort of sets A in some real group, actual group, which are say finite, but such that the product set is small. A dot A is bounded by constant times A. Actually, technically, this isn't quite the definition of an approximate group. This is the definition of a set of small doubling. We actually usually impose a stronger condition. We want A to be symmetric, contain the identity, and we want A dot A to be covered by K translates of A. But essentially, this is the sort of object that we care about. So things like progressions, geometric or arithmetic progressions in a group, or or finite groups and things like that. And again, we have a way of taking limits, much like graph limits actually, which turn approximate groups into neighborhoods of the identity. In a locally compact group. So this connection was first worked out by Khrushchevsky using model theoretic methods, and then later Emmanuel Briard, Ben Green, and myself observed that you just need ultraproducts again. To convert these discrete objects, take a sequence of discrete approximate groups, and in the limit create a continuous object, which would be so. The picture to keep in mind is that you might have a discrete box. Here's a good example of an approximate group, and then you might make it denser and denser and denser. You have a sequence of approximate groups which get denser and denser and denser. In the limit, you should get a continuous square, starting from a discrete boxes that get denser and denser. And there's a general way to do this. And the point of doing this is that there are powerful tools from the subject of topological group theory. that allow you to study these things. In particular, there's this, the solution to Hilbert's fifth problem on how to classify Lie groups topologically. It becomes very, very useful and gives you non-trivial results on approximate groups. In fact, it even classifies them completely. So there's lots and lots of ways to take limits of discrete objects and to create continuous ones. And you can see that there's all sorts of different ways to do it. But it turns out that there is sort of a universal way to take these limits. And the universal way is ultraproducts. I could take all of these. I could have just been ultraproduct of all of these. Okay. There's a single tool, a single gadget, an ultraproduct, which what it does is that it takes a sequence of spaces which in practice would be discrete spaces and produces for you automatically a canonical continuous object, which is you should think of as the limit of your discrete object. And so you don't need to learn you don't actually need to learn all these different ways of taking limits. You just need to learn this one way, and then you can pass back and forth between continuous and discrete fairly easily. So this is what I want to describe. Before I do that, I just want to say a little philosophy about limits. There are actually three notions of limits in mathematics, and most people only learn one or two of them. And which ones you learn depends on whether you're an analyst, an algebraist, or a logician. So just a little bit of philosophy. So what is a limit? So if you're an analyst, the notion of limit that you're most exposed to is that of a topological or metric limit. So here, what happens is that you have some big space X, which is either a topological space or a metric space, and then inside the space you have maybe a sequence, sometimes a net, which is just a fancier version of a sequence. Okay, but yeah, you have some sequence in your set, and you have a notion of a sequence converging to a limit, which in the metric case just means that the distances all go to 0, or in the topological case it means that all the neighborhoods of X trap your sequence. And so this is the standard notion of limit that we're used to, and so like when you write down, say, Hausdorff limits, you build a metric. You know, in graph limits, you usually also build some sort of metric. First, from a correspondence principle, you often use the a topological limit using, say, vague convergence or weak star convergence of measures. So this is a limit which these are the limits that analysts are most familiar with. One thing to note, though, is that to take these limits, all the elements the objects you want to take a limit of have to lie in the same space. So, you have to somehow build a space of all graphs, a space of all dense subsets of integers or something, and create a space out of those. Sometimes that's not so natural. Sometimes all these objects really are living in different spaces, like a graph in n vertices where n keeps changing. Yeah, and I mean, you could just take a big union and make them a big space, but that's not completely natural. Okay, but anyway, these are the limits that analysts usually learn. If you're an algebraist, you usually instead use categorical limits, direct and inverse limits in category theory. So so now your objects might be a set of spaces, a sequence of spaces, and you might have various maps. So you might have a sequence of spaces which all map into each other, like this. Okay, and then and these might be groups or vector spaces or rings or whatever. And very often you can take a limit and create a big space which everybody maps to. Or if the arrows go the other way, okay, you can often build a space going the other way. And you can also have more fancy diagrams than just these chains. Okay, so these are direct and inverse limits. Typical examples are if you take this cyclic group of a prime, this projects the cyclic group of p squared, cyclic group p cubed. And if you just take the inverse limit in the category of rings, you get the p-adics. So these are categorical limits. Algebraists love them. So you can take limits of all kinds of things, but in order for it to be a useful limit, you need lots of maps, morphisms between objects before the useful limit emerges. So categorical limits need morphisms. Topological or metric limits need convergence. Okay, so of course the famous issue, you can't take a limit of just any sequence. Okay, first it has to all lie in the same space, and second it has to converge before you can extract a limit. So ultra limits. Okay, so you can if you use ultrafilters and ultraproducts to create limits, what this does for you is that you can take now elements in any space. You can take elements xn, each of which lives in a different space xn. Okay, and you can form a limit, which won't lie in any of the original spaces. It will lie in the ultraproduct of these spaces, which is a limiting space of all these spaces. But the advantage of ultraproducts is that you don't need any morphisms, as with the categorical limits, and you don't need any convergence. You can take any sequence in any space and you create a limit. And it sounds like that's sort of too good to be true. That you shouldn't be able to. It's too content-free to actually do anything. But what it does very, very neatly is that it converts discrete to continuous, and that allows you to just use all these continuous objects out of the box. Okay, so that's sort of the philosophy. All right, so now I have to tell you what an ultrafilter and ultraproducts are. Okay, and these are not scary objects. These are voting schemes, just on an infinite set. They're very discrete things, actually. They just happen to be on the natural numbers. Okay, so I need to define the notion of a non-principal ultrafilter. Alpha, okay. And, sorry. Okay. And the space of non-principal ultrafilters is called beta n/n, but never mind that. Okay, so a non-principal ultrafilter, what it is, formally, by definition, it's just a collection of subsets of the natural numbers, and these subsets will be called alpha-large subsets. So there's an uncountable number of subsets of the integers, the even integers, odd integers, whatever, prime numbers, so forth. So some of them we're going to call alpha large, and some of them we're not going to call not alpha large. And you want various axioms, and there are 4 axioms that you want. One of them is that no finite set is alpha large. Okay, so only big sets get to be large. Okay, another one is that any intersection, let's say, of two alpha large sets is always alpha large. Okay. Okay. So, all right. Then the third axiom is that any set containing any subset of n containing an alpha large set is still alpha large. Okay, so if you have a set that's already alpha large, you make it bigger, it's still alpha large. These 2 axioms basically tell you that this set is a filter. Okay, and then it's the final axiom tells you it's an ultrafilter, and the first axiom tells you it's non-principal. So the final axiom is that if you take any subset of the integers, then either E or its complement alpha large. Okay, so either the odd numbers or the even numbers, for example, are alpha large, one of the 2. It can't be both, because if they were both, then the intersection would be alpha large, but only the empty set is alpha large, but no finite set is supposed to be alpha large. Okay, so this is a non-principal ultrafilter. It's a mechanism for defining alpha large sets, for large sets. If you like, an ultrafilter is a counterexample to Arrow's theorem for infinite voting population. So once you have an ultrafilter, and if you have an infinite number of voters, each one of which is given by a natural number, indexed by a natural number, then you can set up a voting system that if you have a referendum, right, if you want to vote on something, everyone either votes yes or no, and by the last axiom in particular, one of those, either the yes voters or no voters will be alpha large, and then whichever answer is alpha large, that guy wins the election. Okay, so that's a voting system, and all these axioms tell you that this voting system is sort of rational. That if someone switches their vote from no to yes, then that increases the chance that the outcome is yes, and so on and so forth. Okay, and no finite set is alpha large means there's no dictators. Okay. And you can generalize that. Given any finite set of options, you can vote for any finite set of options, and exactly one of the options will be an alpha large set. So it's basically a voting system with no deficiencies. Right? That all the paradoxes of voting don't occur, and it's because you have an infinite number of voters. Okay, so these things don't exist if you replace this by a finite set. They only exist in an infinite set. Now, at this point, you're supposed to give an example of an ultrafilter, non-principal ultrafilter. But yeah, there's a slight problem, is that these things can only be constructed using axiom of choice. If you drop this no finite set thing, then you can make a dictator. Okay, if all the sets that contain 17 that's an alpha large set. That's an ultrafilter, but it's not as a principal ultrafilter. But those ones we don't use. Yeah. So if you have axiom of choice, these are very easy to construct. Just easy Zorn's lemma argument. Basically, it's a greedy algorithm. But you have to run it at an uncountable length of time. So no finite set is alpha large. So any cofinite set, any set which is complement is finite, is alpha large. So you've already got some sets you declared alpha large. Then maybe you look at the even numbers and the odd numbers. So at present, neither of those have to be alpha large, but you've got to pick one of them. Okay, so you make a choice. Okay, so I choose the even numbers to be alpha large. And that gives you a few more alpha large sets. So any set that contains the even numbers is alpha large. Anything like you remove a finite number of elements of even numbers is still alpha large. But then there's, say, the multiples of 3. Okay, 1 mod 3, 2 mod 3, 0 mod 3. One of them has to be alpha large. You make a choice. You pick one. You throw that in. And you just keep doing this an uncountable number of times, okay? And you make it a huge number of choices, but eventually you create an ultrafilter. Okay, so to build around these things needs the axiom of choice. Now that is a little bit, well, if you're really sort of a finitist, that's sort of unsatisfactory. But one nice thing about there's a nice sort of Gödel that says that any statement which is really finitary, and by finitary I mean that which is phasable. In piano arithmetic, so just in the natural numbers using just addition and multiplication and so forth, like Fermat's last theorem or something. Any statement which is phasable in piano arithmetic. So basically anything finitary which is provable using the axiom of choice, or more precisely in the ZFC set theory axioms, is provable without axiom of choice. So you can use ultrafilters using axiom of choice to prove something, but if what you're proving is finitary, say the triangle removal lemma or Zimmer's theorem or whatever, then automatically it also you can also prove it without choice. Okay, so from a logical perspective, the fact that it uses choice is not an issue. Okay, so all right, so these are non-principal ultrafilters. There's lots of them. There's an uncountable number of these ultrafilters because you have to make the uncountable number of choices. But what one does to take these limits is you just pick one. Okay, so you just choose one non-principal ultrafilter, and it just doesn't really matter which one. I mean, they're not quite all isomorphic, but the finer properties of ultrafilters are not so important for the purposes of taking limits. They're important for other things, but you just pick one alpha and you just fix it for the rest of your mathematics. And so basically, you just pick a voting protocol, okay? And so now you have a way to take votes. You can sample of any you can ask a natural number, the natural numbers, any question you like, and you will get an answer. Okay, so you just pick one, and this protocol obeys all kinds of good consistency properties, and it's for these axioms I was supposed to tell you. Okay, so now once you have the ultrafilter, you can start taking limits. So as I said, if you have any finite set, and if you have any sequence in a finite set, so you have a finite number of choices, okay, and every natural number picks one of those choices, then there's a unique limit in the space, the outcome of your election. So you define the ultra limit of this sequence in a finite space, a coloring, if you wish, to be the color or vote or candidate which acquires an alpha large set of voters. Okay, and there's always exactly one. Okay, so you have a notion. You could, any sequence any sequence taken with a finite range has a limit. Okay, there's a notion of convergence. Okay, I mean, if it does converge, like, then if this converges in the classical sense, like if this xn is eventually constant, then this limit will agree with the classical limit because of no finite set is alpha large. But but it generalizes the limit. Like, it extends the limit. It's just like the Banach limits, if you know what they are in constructing the Hahn-Banach theorem. They're very similar, actually. Okay, so for any finite set, you can take any sequence which is finitely valued has a limit which is still in that space. Okay. Now, what if x is not infinite? What if x is infinite? So suppose now you have a sequence taking values in an infinite space. Well, actually, the way I'm going to think about it is that actually, suppose every element in your sequence just takes values in a different space, and maybe xn takes values in the space of graphs of n vertices. Okay, so you make a sequence of graphs of n vertices where n gets bigger and bigger. Each xn is finite, but the union is infinite. Now, in this case, the limit, usually when you have an infinite space here, there'll be no single xn which comes up in alpha large set of time. So normally you won't have a limit in this space, but what you can just do is that you can still define a formal limit. So you just formally define to just be a mathematical object. Formally, actually, if you want the precise definition, you define this to be the equivalence classes. Of all other sequences which agree with this sequence, where you see that two sequences are similar if xn is equal to yn for an alpha large set of n. Okay, this is the formal definition, but you shouldn't pay too much attention to it. It is analogous to how you construct the real numbers in classical analysis. So you start the rationals and you want to build the reals. One of the standard ways to build the reals is as the Cauchy completion, metric completion of the rationals. You can define the reals as equivalence classes of Cauchy sequences, rationals. Okay, where two rational sequences are equivalent if their differences go to 0. Now, this is a formal way to define the reals, but no one actually uses this definition. I mean, that's only for foundational purposes. Okay, but the important thing is that the reals exist. Okay, and that they complete the initial. So never mind this. Okay, the thing is that you just formally define a limit. Okay, and two sequences have the same limit if they agree eventually on an alpha large set. That if the voters agree that they're the same. Okay, so this is just formally how you define a limit. And if the xn's live in all these spaces, the set of all such limits for the ultraproduct. The xn's, and it's called, there's various notations, but I'll call it product of alpha n as n tends to infinity. So sort of a limiting object. Okay, so in the finite case, if you just take the ultraproduct of a finite set, you will just get back the same finite set. That's the only thing that you can get. If x is finite. If x is infinite, you take the ultraproduct of a set of itself. This is called the ultrapower of x. This is called the ultrapower. And it's strictly bigger than x. Okay, so if you have a constant sequence, then your limit is that constant. But you can have non-constant sequences, which will take values in outside unitional space. So just like if you take limits of Cauchy sequence of rationals, sometimes you might get irrational, but usually you get irrational. Usually you'll get a bigger space. Okay, so this, so just like the rationals will complete to the reals, every space gets completed to a bigger space here. So, for example, the natural numbers now live inside the ultrapower of the natural numbers. So these guys are called the standard natural numbers. These guys are called the non-standard natural numbers. Yeah, so among other things, ultrapower ultraproducts are used to build non-standard analysis, but it's not really a scary term. It's just a non-standard object is just basically an ultra-limit or ultraproduct of standard things. So, for example, the limit of sequence n, 1, 2, 3, 4, 5, 6, okay, that doesn't exist in the classical sense, or you could say converges to infinity or something. But this is not a standard natural number, but it is a non-standard natural number in this bigger space. Okay, and in the reals, also some of them live inside so these are the standard reals. These guys are the non-standard reals, also called the hyperreals. And you can have things like the limit goes from 1 to n, 1 over n. This is not 0. Because 0 and 1 over n disagree for every n. So the voters will see that 1 over n and 0 are not the same space. It's what's called it's a non-standard real. It's what's called an infinitesimal real. It's not actually 0, but it's infinitesimally close to 0. It's the reciprocal of this natural number, actually. But okay, which is an unbounded natural number. Okay, so you can build all these objects. Okay, so already just from that you can formally take limits of everything on the left and get something which is. I mean, it's a sort of triviality, but like if you have a sequence, for example, of graphs, of finite graphs, then just from this ultraproduct construction, I can build for you an infinite graph. Okay, just out of this. So V alpha is what it is just the ultraproduct of the n's, and the E alpha is just the ultraproduct of the. Okay, so in this limiting graph, the vertices here are just ultra limits of sequences of vertices in the original graph, and any edge is just a pair. Each one of which is an ultra limit it's a bit of pairs coming from the original graph. So automatically you can take ultra limits of anything. Okay, polynomials, varieties, whatever. But why would you do this? So the first observation is that any operation that you have on your original discrete objects carries over to the continuous world. So suppose, for example, you have a group. You have a sequence of groups. So you've got a multiplication operation, also an inversion operation. This is the same multiplication. Okay. A finite group, say. Okay. So you can take a sequence of finite groups, and then you can take the ultraproduct. Okay. So this is the set of all formal limits of group elements, one from each one group. So you got maybe one group here, another group, and somehow you take every single sequence and you get this sort of limiting point here, and there'll be this really huge uncountable limit. But the thing is, it's still a group. You've still got an operation on it. Just like once you define, say, addition on the rationals, and then you complete it, you can define addition on the reals just because addition is continuous with respect to Kashi sequences. If you have two elements in this limit group, so what is that? So one of them would be the limit of one sequence coming from your finite groups, and then you got another limit coming from another sequence. Okay, and you just define the group law on this limiting object. What you do is you just go back to the finite world, you perform the group multiplication here, and then you take ultra limits again. Okay. And this is just how you define multiplication. And there's no issue of convergence because everything converges. Okay, so this just works. Okay. One thing you have to check is that things are equivalents. Like if you replace this sequence with an equivalent sequence and this equivalent sequence, this product is still equivalent, but that just follows from the ultraproduct axioms. Okay, so you can define any operation basically that you already had in the finite world still will still hold will still be there in the limit, and the great thing is that any axiom that you already had in the finite world will automatically persist to the infinite world. So the group law is associative in the finite world, and it's very easy to see that therefore in the limit the group law is still associative. So the ultraproduct of any sequence of groups is still a group. Ultraproduct of fields is still a field. Ultraproduct of algebraic closed field is still algebraic closed field, and so on and so forth. In fact, there's this great thing called Lorsch's theorem. What it basically says is that if you have any predicate on some finite number of variables, and maybe also some constants. And these will take values in some finite space. So I guess you've got to index these things. Okay, so if you have any predicate at all, like the associativity law or the inverse law, or whatever, using some constants and some variables quantified over in some language using the for and there exists and everything quantified in the space. If this predicate is true, for an alpha large set of n, then when you take ultra limits of everything, okay, if you take the ultra limit of these variables, and these constants and so forth, and now you're working in the ultra limit space, then this thing will be true. The same predicate will be true in the ultra limit space. And conversely, if it's true, then this has to be true for an alpha large set of n. So never mind exactly what this is, but basically it means that anything you already knew about for the original standard spaces are also true in the limit. So, for example, in the natural numbers, Fermat's last theorem is a theorem, so automatically the Fermat's last theorem is also true in the non-standard natural number. So I can tell you that there's no non-standard number bigger than 2, such that x to the n plus y to the n. For some positive, for some strictly positive x, y, z, where these are all non-standard natural numbers, so ultra limits of natural numbers, things like this, which are unbounded. Okay, I know that the standard natural numbers contain infinitely many pairs of primes 600 distance apart. The same thing is true for non-standard natural numbers, and so on and so forth. Okay, so you don't really lose anything as long as it's describable in first-order logic. Yeah, of course. For example, anything which is not describable can be lost. So, like all these groups are finite, but in the limit, you get something that's not finite. But being finite is not a first-order predicate. Okay. So you have these limits. Okay, so maybe I should give you an example of how you actually use this machinery. Okay, so I'll give you a very simple example first, and then I'll give you a more advanced thing. So actually, there was a talk yesterday talking about the polynomial regularity lemma. Maybe I'll start there. So this is a very simple thing, but it already illustrates some of the ideas of how you actually use these limits. So, okay. Okay, so let's be now very concrete. Let's take a field F, which I think was a finite field. Okay, yeah, some dimension D. Actually, no, I need. Okay, let's call the dimension capital N. So natural number. Okay, and let's define polynomials of degree D. On Fn. Okay, so these are just polynomials from Fn to F of degree. So if D is 2, these are like all the quadratic polynomials on this finite field vector space. So, F doesn't have to be finite, but you can think of it as finite. Okay, so we have this notion of rank. So if you have a polynomial in here, you can define, as we saw yesterday, the D minus 1 rank of P is the fewest number M of degree D minus 1 polynomials, of degree, let's say, less than D minus 1 polynomials. Q1 up to Qm, such that P is a function. Okay, so if you can write your polynomial, your degree D polynomial in terms of a finite number of degree D minus 1 polynomials in your finite rank, and the smallest number of polynomials you need is the D minus 1 rank. Okay, so we saw that before. In a finite field, these ranks are always finite. In an infinite field, you can have polynomials of infinite rank, but let's never mind that. Okay, so here let me give you a simple case, actually just the first step of the polynomial regularity lemma. So, okay, so I haven't said the lemma yet. Okay, so what is the lemma? It's the quantitative version, which is the version we actually use. There is it. Okay. So suppose you have a bunch of polynomials D field, So given any polynomials, they may or may not have low rank or high rank, but okay, so you have some polynomials. I also need a function, arbitrary function. Think of it like an exponential tau exponential function. Some rapidly growing function. Then I can always find a good basis. I can always find another set of polynomials. And these are there'll be fewer of these. This number of b's is at most a, such that every pi, or every I, this and also a number m, and m is some bounded number bounded by f. Okay, there's some number m, bounded only by this function f. It's of a tau exponential in f, basically, such that for all for I, every pi can be written as a linear combination of the qj's plus an error, and this error has bounded rank, the rank of these errors. Okay. So I can find a good basis of polynomials such that the original polynomials can be written as a linear combination of these are just coefficients, plus an error of bounded rank, and that these guys are independent in the following sense, that any non-trivial combination. So if you take any non-trivial combination of these coefficients, of these polynomials, then these guys always have big rank. And in fact, very big rank, bigger than the function f applied to m. So in practice, you should think of f as being like a tau exponential. So these errors are of rank at most m, but these guys have rank bigger than 2 to the m or whatever, something really, really big. Okay. And so, okay, this is the actually the first step of the polynomial regularity lemma. In practice, you keep going. You take the polynomials, the d-1 degree polynomials that show up here, and you have to regularize them further to d-2 polynomials and so forth. But let me just ignore all the remaining steps of the process. Okay, so this is a lemma. It's not hard to prove, as was stated actually yesterday. It's a very simple algorithm. You take these p's, polynomials, and either they're already sort of independent in the sense that every non-trivial combination already has really big rank. Okay? If they are independent like that, then you're already done. If not, one of them is going to be written as the combination of the others plus a bounded rank error. So you remove that polynomial, put it in terms of all the others, and now you ask, are the guys that are left, are those independent, and so forth. But you have to keep track of all these quantitative things. What's the rank of all the errors and so forth, and it's a little bit fiddly. It's not difficult, but to actually write it out in full detail, it's just it's a page. But you have to keep track of this m and this f, and it's a little bit fiddly. Okay. On the other hand, if you don't care about bounds, then it's really simple. So here's the qualitative version of the same lemma. Qualitative regularity. So you have a field which now can be infinite. Take a bunch of polynomials in that field. Okay. Now there's no function. Okay. So the qualitative version is that given any bunch of polynomials, I can find another set of polynomials with fewer, a subset actually of the original set, such that every polynomial is a linear combination plus an error of not just finite rank. Okay. Okay. So up to now finite rank rather than bounded rank. There's a subtle difference here. Okay. That every polynomial is a linear combination of these polynomials, and these polynomials are independent modulo lower rank errors. So. For all non-trivial. So. Okay, so any combination of these now has infinite rank rather than bigger than this f of m. Okay, now this lemma really is this lemma is just an immediate consequence of standard linear algebra. See, so a basic theorem in linear algebra is that if you have a bunch of vectors in a vector space, then you can always find a subbasis which are linearly independent, okay, such that everybody here is a linear combination of everybody here. Okay? I mean, this theorem doesn't even have a name. It's still trivial. Okay? Every space, every set of vectors has a linear independent basis. Okay, and this lemma is you just apply that lemma, and to what? What you do is that you take the polynomials of degree d, and you quotient out by the finite rank polynomials. See, the great thing about working in the qualitative world rather than the quantitative world is that the sum of two finite rank polynomials is still a finite rank. And so the set of all finite rank polynomials is a vector space, and you can quotient by it. And this is something you do in continuous mathematics. You take quotients. You want to do this in the discrete world. It would make your life easier if you could quotient out by all bounded rank objects, but you can't quite, because it's not quite closed-under addition. Sum of two things of rank m is a rank 2m. And so you don't have a single space of bounded rank objects. You just have sort of this whole nested sort of family of spaces. But in the quantitative world, you just have one, the finite rank polynomials. And so you just take the original polynomials, quotient out by finite rank. This is in a vector space. Linear algebra tells you there's a basis there. Pull it back, and it gives you this theorem. Okay, so you don't have to work. Okay, you have to use a very trivial linear algebra fact. Now, okay, so. Now, this thing looks weaker than this theorem. Of course, if you have the quantitative lemma, then it's very easy to deduce the lemma. But these are actually equivalent. Okay. Once you have the qualitative regularity lemma, you just use an ultraproduct. And you automatically get the finite tree thing too. So let me see if I can do that. Eesh. Okay. This was supposed to be one of several examples. Okay, but I only have one. Okay. All right. I was going to show you the semi-regularity lemma in the ultraproduct method. That was probably the most interesting. Because this is fairly simple, but this was sort of a warm-up. Okay, so suppose you know the qualitative regularity lemma. Why is the quantitative regularity lemma true? Okay, so you argue by contradiction. Okay, so suppose quantitative lemma is false. Okay, so then you've got to negate all these quantifiers. So yeah, it's a bit messy, but what you find is when you carefully negate everything, what you find is the following. This means that there is no bound. This statement is not true for any bound on M. So okay, so that there exists a function such that no matter how large a bound you pick, you can find a field, Fn, and dimension, I guess, Nn. Okay. Okay, you can find a field, you can find a dimension, you can find a set of polynomials. Okay, A, so that then you can find a set of polynomials. In this vector space, such that you can't do this. Okay, such that for no. Okay, yeah. Okay, this looks complicated, but it's very straightforward. That once you get a practice with this, it's always automatic. You just follow your nose, and it will always work out. But okay, the first time to do it, you have to be rather careful. So you can find a bunch of polynomials such that no matter what m you pick up to the specified range, there is no q1 up to qb A such that these things are true. Okay, but maybe I'll just call this 1 and 2. Okay. 2. Okay, so when you actually negate this, when you negate this statement, you get a rather complicated assertion. But okay, you get something. So basically, but the general philosophy is that you take a quantitative statement, negate it. Then once you have this counterexample, you take the ultraproduct of the counterexample, and that will give you a counterexample to this lemma here. So maybe I won't do it, but okay, so you. So you have a sequence of fields. You take an ultraproduct, you get another field. Okay, you take this and you take an ultraproduct of these vector spaces. You get a big vector space over this field. You take the ultraproduct of these polynomials of degree d. You get another polynomial of degree d over this much bigger vector space. Okay, maybe I won't do it, but I'll just you can just believe me that if you take the ultraproduct of everything that I just wrote down here, you will get a counterexample to statement here, and hence, because this is true, this has to be true as well. Okay, so it's still the same proof. Here how do you prove this lemma that every finite set of vectors has an independent basis? You run the same algorithm that you do to prove the quantitative thing. That if they're independent already, you're done. Otherwise, one of them is in some of the others, and so forth. But the thing is, this is already in the literature. Right? You don't actually have to use this to explain the argument again. You can just use it as a black box. And you have these convenient things. You take quotients and so forth. I mean, so it's repackaging the same argument, but in a sort of clean conceptual way. You don't have to worry about exactly what low rank and big rank mean. It's all done automatically for you. Okay. All right. I won't have time to regularity lemma, unfortunately. I think I can do the correspondence principle. Okay, maybe I'll just end with that. Okay, so Zimmerman's theorem. Okay, so what's okay? Zimmerman's theorem, I'll phrase it like this. So for every k and every delta, there exists an n, such that for all subsets. Or sufficiently large n, actually, and sufficiently large, actually. Such that there's a subset that every subset of integers from 1 to n of density at least delta n the k-term arithmetic progression. Okay, so this is Zimmerman's theorem. Fürstenberg proved this theorem by proving a measure theoretic analog. So for every k and every measure preserving system x. So a measure preserving system is a probability space with a shift which preserves measure. Okay. So if you have any space x with a measure, probability measure, and a shift on it, and any set of positive measure now. So there's no delta anymore, it's just positivity. It's a more qualitative statement. Then you can find a positive number n such that a and the shift of a and the shift of a few more times also has positive measure. Okay, so given any set a, it's possible to shift it again and again so that the intersection is still non-empty. It still has positive measure, and in particular it's non-empty. Okay, so this is a theorem that you can prove by ergodic theory methods, but you don't need to know how it's proven. If you're willing to accept it as a black box, this theorem, again, is actually equivalent to Zimmerman's theorem. If you have Zimmerman's theorem, it's easy to prove this theorem. You look at a typical orbit of a point, and the typical orbit will be like a dense set. So you can apply it as Zimmermann. But conversely, you can use this qualitative result to prove this quantitative result. And the way you do this is that, okay, so if this is true, suppose not. So suppose Zimmermann's theorem is false, then exists a k and a delta, and a sequence of n. There'll be a sequence of numbers going to infinity, and a sequence of an inside these intervals nn of all of positive density, such that no an can exist at kap. So you've got a sequence of counterexamples which are getting bigger and bigger, okay? But all have a uniform lower density. And it's possible to take an ultraproduct of everything. So these n's will, you take an ultraproduct, and you'll get a non-standard natural number. So you've got the natural numbers, and then you've got these much bigger sort of double position natural numbers, if you wish. Okay, long natural numbers. Okay, and okay, and you take the ultra limit, and so you get this really big non-standard natural number, which is bigger than all the standard ones, and you get a subset of. Okay, so you have this big interval now, and you've got this big subset here, A. Now, each of these finite intervals here comes with a natural measure, which is the normalized counting measure. So on these NNs, there's a natural measure, which is just the density measure. So that's a probability measure on this space. There's a way to take ultraproduct of measures. Now, you have to be a bit careful because measure theory is not a first-order theory, and you have to use the categorics. You have to use actually a bit of measure theory to do this. But okay, but it is possible to construct a measure, a probability measure on this space, which in some sense is the ultra limit of the ultra measure set. I won't explain how that works because I don't have time. But it's called load measure. I'll look it up. Okay, so there's a nice probability measure on here, which is in some sense the ultra product of all the measures here. And so all these sets of positive density, if you take the limit, you get a set, and it will still have positive density. It will still be measured bigger than delta, as it turns out. Now, why do you pass this limit? The thing is, over here on the limit, you have a shift. X goes to x plus 1, which isn't quite well, yeah, and then you wrap around. If you go over here, you wrap around to 0. And the thing is, well, actually, it only needs to be defined almost everywhere. Okay, so actually, you don't define it at the endpoints, but the endpoints have measure 0, 1, 0. So outside it says measure 0, the shift is well defined. And this is a measure preserving system. You see, on any finite interval, the shift is not measure preserving because every time you shift by 1, somebody falls off the edge. Okay, and so you lose a little bit of measure. But in the infinite world, or once you go to this non-standard world, you up to such measure 0, you are invariant, and Furstenberg's theorem can tolerate losses on such measure 0. And so you've now constructed a measure preserving system, and and it's not hard to show that this sequence of counterexamples in the limit gives you a sequence of counterexample to Furstenberg's. So what you see is that every time you want to move a quantitative statement about finitary things, you assume it fails, you have a sequence of counterexamples, you take an ultraproduct, and this will be a counterexample to some continuous statement. And if you just prove that continuous statement, then you've proven your discrete thing. And you can do this for all kinds of other things, like the regularity lemma and so forth. But that I think, well, if you're interested, I can tell you in person. But I think
We have a few minutes for questions.
Who first came up with all topic?
I have no idea, actually.
After this.
Hmm?
No.
I mean, it's very old topic. I mean, Bourbaki used them all the time, but they weren't the first, certainly. Don't know.
Actually, I'm one of the people who originally defined ultraproducts in the late 50s under the influence of Tarski.
Okay.
We didn't understand Lerm's paper at the time because he wrote it in terms of Boolean algebras, but then later we defined ultraproducts. And I was the first person to prove the compactness theorem.
Okay.
With which you made use of.
Yeah, it's implicit. Yeah, I didn't have time to talk. Yeah.
So it's a little weird after 55 years to hear a lecture about ultraproducts. I'm glad you're bringing them back to people's consciousness because there are a lot of uses of them, and of course the work of Jerry Kiesler and his collaborators was very, very important. And you referred to the Lerm measure there.
It's a special case of Kiesler measures construction. Yeah.
Basic discovery, and so I hope people will find other applications.
Oh yeah, yeah. Oh, there's a whole bunch of useful stuff. Yeah.
So this was Dana Scott.
Okay. Okay, that answers your question. Look at you.
Yeah, you refer to a theorem of Gödel that if a finitary statement is provable in ZFC, then it's provable in
Yes.
yeah?
Yes.
Does it have a constructive proof? Is there an algorithm given at ZFC?
It's literally constructive. Okay, so in the sense that the way it works is that you work in a universe in which you only have ZF and not ZFC. And then inside that universe, you can build what's called the constructible universe. Roughly speaking, that's all the things that you can define uniquely with predicates. And even if your external universe doesn't obey choice, then this new sub-universe that you construct does obey choice. I think it's the constructive universe. It's either V or L. I can never remember which one is which. Okay, but
well, it's even better than the first order properties. It's Schoenfield's absoluteness lemma.
Well, yes.
And some second order properties are preserved as well. So
that's true. I don't know. Yeah, I don't know how that one's proven though. That's a more difficult theorem. Yeah, but yeah. So there's a sub-universe for which you actually have choice. So and it turns out that the natural numbers are the same in both universes. And so whatever you can prove in the big universe, you can prove in the small universe.
So when you deduce the finitary theorems from the infinite theorems, you don't get any effective bounds on parameters.
If you use the infinity theorem as a black box, then you get absolutely no bound whatsoever. In practice, though, if you actually open the black box and you look at every single step in the proof of the infinite, then usually every single step in the infinite world has some analog in the finite world. The analog will be much messier. There's a lot more epsilons and quantifiers, and every time you take a limit, you have to instead run an algorithm, and there's a lot more looping. But so you can unpack. And so, roughly speaking, if you can prove the infinite statement, using a proof of somehow complexity n, then you can get a bound which is somehow like a tower of height n or something. There's some relation between the difficulty of the proof of the infinite statement and the bounds that show up. But typical things are tower exponential. Right? The rule of thumb I have is that if you're trying to find a result and the only bounds that you hope to get anyway are tower exponential, then you may as well go to the infinite world because you're not losing much by but if there's a chance for polynomial bounds and so forth, then usually you don't want to use the infinite world to prove those. You want
so the fact that you generally get a tower of exponentials, is this kind of an empirical thing, or is there a general?
There are these thing called proof mining that the proof theorists have to. I don't know the precise statements, but roughly speaking, it's how many times you have to do things like take limits, or take spans, or take completions. So, for example, here in the polynomial regularity example, often what you do in continuous world is that you have a finite number of generators, or some small set of generators, and you just look at what this generators span. You look at all the combinations, and you take a completion. Every time you actually use one of those completions, that will cost you some tower when you go back to the finite world. I mean, it's something that you do almost without thinking. You just you take spans, take completions in the continuous world. That is often what's expensive. Yeah.
Do we have any notion of rate for the ultra limit? Would it be meaningful to have such a notion?
Well, I mean, you can use various infinitesimals to gauge rate. So, like if you have a sequence of numbers that converge to zero classically, in the classical sense, then if you take the ultra limit, then the ultra limit is not zero, it's what's called an infinitesimal. Okay, but there's different ranges of infinitesimal. So, for example, if I let epsilon be the limit of 1 over n, okay, so this is an example of infinitesimal. This infinitesimal will be less than epsilon if xn is eventually less than 1 over n. If it's less than 1 over n for an alpha large set of n, then this is less than, okay. But, so for example, the sequence 1 over n squared is less than epsilon. Okay, but you can ask, are you less than epsilon squared? And that measures a faster rate. Or are you less than e to the minus 1 over epsilon? And that's an even faster rate. So rates of convergence become replaced by just comparison with various infinitesimals. Yeah. Yeah, so when you go to the non-standard world, you don't see limits anymore, because somehow all the limits have already been taken. Right? What an ultra limit is, it takes all your limits for you at once at the beginning. And then calculus and analysis becomes sort of algebra. Saying that one sequence is eventually bigger of another is just saying that one is less than a constant times the other.
I'd say we thank Terry again for a very inspiring